Imagine you walk into a lab, and instead of a machine printing plastic, it is printing living tissue. Not a phone case, not a toy dinosaur. Skin. Cartilage-like structures, tiny living constructs built layer by layer from biomaterials and cells. That is not science fiction. That is bioprinting. And yet, before we all start ordering custom kidneys with same-day delivery, there is a brutal catch. While bioprinting has made real progress with tissues and experimental constructs, full, transplant-ready complex organs remain experimental, largely because living organs need vascular networks, structural integrity, long-term function, and safe clinical translation all at once. Tonight, we go deep into one of the strangest frontiers in science, the quest to turn a printer into a biological architect, a machine that does not ask, "What shape shall I make?" but "What shall I bring to life?" Let me tell you a story. For most of human history, if part of the body failed, medicine had only a few options: stitch it, splint it, cut it out, or pray over the bill. If skin was badly burned, if cartilage wore down, if an organ failed, doctors were forced into a cruel economy of scarcity. You either borrowed tissue from somewhere else, waited for a donor, or learned the ancient medical art known as "let's hope this works." Then, humanity invented 3D printing. At first, it was mostly plastic, useful, clever, kind of nerdy. Then someone looked at the printer and asked the most dangerous question in science. What if the ink were alive? That question launched 3D bioprinting, the layer-by-layer placement of cells, biomaterials, and signaling components to build tissue-like structures for research, repair, and one day, perhaps, replacement. Modern reviews describe it as a core platform in tissue engineering and regenerative medicine, with especially active work in skin, cartilage, bone, vascular models, and organoids. What bioprinting actually is. Now, pause right there, because this is where many people imagine a machine printing a finished liver like a vending machine drops a soda. No. Bioprinting is not Control-P for organs. It's more like trying to build a city out of jelly while the bricks are alive. The roads must carry nutrients, the power grid has to self-organize, and the citizens die if you squeeze too hard. A bioprinter usually works with something called a bioink, a printable mixture that may include living cells, hydrogels, growth-supporting materials, and biochemical cues. The printer deposits this material according to a digital design, often layer by layer, to create a 3D construct that then has to mature, stabilize, and function in a biological environment. So the drama is not just printing the shape. The drama is preserving cell viability, getting the right mechanical properties, and convincing the printed structure to behave like tissue rather than wet optimism. Reviews of current bioprinting repeatedly identify bioink optimization, maturation, vascularization, scale-up, and reproducibility as major hurdles. In other words, printing life is hard. Life, very rudely, insists on being complicated. Why skin and cartilage are leading the way. Here's where the story gets exciting. Bioprinting has been most convincing not in fully printing giant transplant-ready organs, but in building simpler tissues and useful constructs. Skin is one of the clearest examples. Recent reviews describe substantial progress in skin equivalents and wound healing applications, including approaches that mimic multiple skin layers and explore vascularization, pigmentation, and regenerative function. Why skin? Because skin, while biologically sophisticated, is more approachable than something like a kidney. It has layers, structure, and healing complexity, but you do not need to recreate the full biochemical madness of an organ that filters blood every second of your life, like an overworked accountant on espresso. Cartilage is another promising battlefield. Recent literature shows sustained progress in cartilage and osteochondral bioprinting, with studies and reviews focusing on scaffold design, bioinks, and cartilage-like constructs for repair and research. And cartilage has one huge advantage in this story. It's not heavily vascularized like major organs. That matters because one of the great enemies of bioprinting is blood supply. A printed cartilage-like structure doesn't immediately face the same oxygen and nutrient logistics nightmare as a thick, metabolically active organ. The vascularization challenge is widely described as one of the central barriers to fabricating larger, more complex living tissues. So yes, the headline is real. Skin, real progress. Cartilage-like structures, real progress. A fully printed replacement heart for your uncle who still eats like it's a competitive sport. Not there. The vascularization nightmare. Let's descend into the rabbit hole. Suppose you print a thick piece of tissue, beautiful shape, good cells, elegant design. It looks magnificent for about 5 minutes. Then biology leans over and says, "Lovely, where are the blood vessels?" This is the core problem. Cells deep inside a thick construct need oxygen and nutrients, and they need waste removed. In the body, blood vessels handle this logistics empire. Without adequate vascularization, thicker tissues struggle to survive and function. Reviews on organ bioprinting and vascularization keep coming back to this point. Making vascular networks that are printable, perfusible, stable, and clinically useful is one of the field's hardest challenges. And now the problem gets worse. An organ is not just a chunk of cells with plumbing. It's architecture, plus chemistry, plus mechanics, plus electrical or metabolic coordination, plus immune compatibility, plus durability. A heart must beat. An organ must metabolize. A kidney must filter with exquisite selectivity. A lung must exchange gases across a vast, delicate surface without collapsing into biological soup. So when you hear scientists printed a miniature liver, celebrate. But don't confuse that with hospitals can now print a fully functional replacement organ on Tuesday. That leap is enormous. Current roadmaps and reviews emphasize that full organ fabrication faces intertwined barriers involving vascular complexity, innervation, maturation, scaling, biomaterials, function, and regulatory translation. What bioprinting is already good for? Now, here's the twist that makes this story even better. The field doesn't need to wait for a printable kidney empire to become useful. Bioprinted tissues already matter because they can be used for research, drug testing, disease modeling, and preclinical platforms. NIH and FDA-linked materials describe 3D tissue bioprinting as an important platform for predictive efficacy and toxicity assays, while reviews also highlight in vitro tissue models and organ-mimicking constructs as major near-term applications. This is huge because maybe the first revolution isn't, "Here's your printed pancreas, have a nice day." Maybe the first revolution is, we can test drugs on bioprinted human-like tissue models instead of relying so heavily on cruder systems. That could improve screening, reduce attrition in drug development, and create more realistic disease models. Some scientific and policy discussions also point to these systems as part of the broader move toward new approach methodologies in biomedical testing. So bioprinting is already powerful even before it reaches the organ replacement endgame. That's the part most sci-fi headlines skip because printed human spleen changes everything. How the printer becomes a biological chef. Let's make this visual for the audience.
A normal 3D printer is like a robot pastry bag that squeezes out material in layers. A bioprinter is similar, except the frosting contains cells, the cake has to stay alive, and if you overbake it, congratulations, you invented expensive sadness. There are multiple bioprinting approaches, commonly including extrusion-based methods and other deposition strategies, each with trade-offs in resolution, speed, cell stress, and material compatibility. Across recent reviews, extrusion remains especially prominent because it's flexible and accessible, though it can expose cells to mechanical stress and often sacrifices resolution compared to some alternative methods. And then comes the bioink puzzle. Too soft, the structure collapses. Too stiff, cells hate it. Too thick, it won't print well. Too thin, it oozes like biological pancake batter. So the field is constantly negotiating a three-way truce
between printability, biocompatibility, and function. Recent reviews repeatedly frame bioink design as a central determinant of clinical translation. This is why bioprinting feels like a marriage between engineering and biology. One spouse says it must hold shape. The other says it must stay alive, and both are looking at the budget. Why full organs remain experimental? Now let us answer the big question with total honesty. Can we print whole human organs today? We can print organ-like constructs, experimental tissue models, vascularized prototypes, and increasingly sophisticated structures. But full, clinically routine, transplant-ready complex organs are still experimental. That is the sober consensus running through current reviews of the field. Why? Because a real transplant organ must clear an absolutely savage checklist. It must survive printing. It must organize correctly, it must connect to blood flow, it must perform the right function for long periods, it must avoid catastrophic structural failure, it must behave safely in the body, it must be manufacturable reproducibly, and then it must survive regulatory scrutiny, clinical trials, storage, transport, implantation, and long-term follow-up. That is not one problem. That is a federation of problems wearing a trench coat. Recent roadmaps and reviews explicitly describe clinical implementation as limited by scale, vascularization, innervation, tissue maturation, immune and biomaterial issues, standardization, and regulatory pathways. So whenever someone tells you, we're basically printing full organs now, give them the scientific translation. No, we are building remarkable stepping stones. The part that feels like the future. And yet, you should still be amazed, because humanity has reached the point where we can digitally design living constructs, position cells with intent, and engineer tissue-like forms that would have sounded insane to previous centuries. This is not a wizard story. This is a manufacturing story, a biology story, a material science story, a what if healing could be fabricated story. Skin regeneration work is advancing. Cartilage and bone-related constructs are improving. In situ bioprinting, printing directly at or for tissue repair sites, is being explored for regenerative medicine applications. Meanwhile, organ bioprinting research continues to push on vascularization and functional complexity. So the future may not arrive as a single dramatic moment where a surgeon yells, "Print me a liver." It may arrive in stages. First, better lab-grown tissue models, then better grafts, then better repair patches, then partial functional constructs, then more complex hybrid tissues, and only after many brutal years of work, perhaps, fully implantable organs. That is how real revolutions usually happen, not with one perfect miracle, but with a staircase. So here is the deepest truth in this entire story. 3D bioprinting is not impressive because it has already solved organ failure. It is impressive because it has turned one of medicine's oldest dreams into an engineering problem.
And engineering problems, given enough time, enough minds, and enough funding, have a habit of becoming history. We are not yet in the age of printable human organs on demand, but we are absolutely in the age where living tissues can be fabricated, studied, improved, and pushed closer to reality than ever before. That is not the end of the story. That is the beginning of a very strange chapter, where the printer stops being a machine for objects and starts becoming a machine for healing. So the next time someone says scientists can print organs now, you can smile and say, not exactly. They can print meaningful living tissues and experimental constructs. Skin and cartilage-like structures are real areas of progress, but full complex organs, still experimental, still difficult, still coming. And honestly, that truth is more fascinating than the hype, because real science is not magic. It's better. It's humanity, layer by layer, learning how to build life without pretending the blueprint is simple. If this kind of story blew your mind, subscribe, because this channel is where we chase the line between science fiction and science fact until the line breaks. Type "print life" in the comments if you want the next episode.